Okay, everyone. So welcome to our third session of the weekly beer general intellect brain of the firm reading group. And this time we are covering chapter 3, the dimensions of the problem. So in the introduction or the summary, Beer says, in chapter 3, we start to use the tools. Here, the really fundamental problem of management is discussed and analyzed. It is the problem of complexity. How to measure it, how to manipulate it. We think of our problems as concerned with such things as men, materials, machinery, and money, and their interaction. It is just that interaction that causes the difficulties, and we must get at its nature. We must also get at the nature of the way huge numbers of states in a system soak each other up, which is the subject of Ashby's law. It turns out that organization exists precisely to implement that cybernetic law. By the end of chapter 3, the fundamental reason should be clear why things cannot be organized down to the last iota, and why, in human terms, we should not even want to try. Of course, we all know that they cannot be so organized, that indeed an awful lot of things just organize themselves. But when we know exactly why, we can approach the problem of how. All right, so the dimensions of the problem being the problem of complexity. Anyone have some general thoughts about chapter 3 to mention?
I think one of the things that chapter 3 is trying to do is Beer had previously written a book called Decision and Control. And so he's trying to condense the ideas from decision and control into the beginning of Brain of the Firm. When he uses the terms decision and control in this chapter, he's using them in the specific context of what they mean in the previous book.
All right. Can you just, sorry, somebody isn't using headphones. I'm getting feedback.
I'm not, so let me switch to headphones.
Okay, thanks. So while we're waiting, anyone else have some comments about chapter 3?
I was just going to say real quickly.
Yeah, go for it.
Okay, go ahead, Rudy.
I forgot to raise my hand, even. My bad.
Yeah, I think this chapter really very well lays out the problem of control, right? That there's no way you can build a machine that can account for everything unless you reduce variety somehow. And I think that's what I got from this chapter.
Yeah, absolutely. When it gets to like the quantum discussion and the processing capacity of matter, that really lays it out quite clearly. Shane, you were going to say something?
Yeah, I mean, it's kind of a similar sort of remarks, but I found that this chapter was quite a bit kind of easier than the previous ones. Like it's getting really into a particular single topic. And the thing that stands out, is that like we're getting to the like Ashby's law thing of like the varieties or the dimensions of the complexity have to balance out in both, like, so that everything needs to be sufficient to the task, whatever the task happens to be. So for a given input, processing input arrangement, it all kind of needs to work out. So you need enough variety in the sensors to discriminate the complexity that you care about. You need enough variety in the processor to process the input. And then you need enough variety in the output to be able to affect anything. And Ashby's law is, in retrospect, it feels almost trivial, and yet it's kind of mind-blowing, And it's also mind-blowing that this is not really something that's well understood generally. I think that's a point that Beer, I don't think he raised it in this book. I think it's more in Heart of the Enterprise, where he says that, like, Ashby's law is like, it's like laws of motion, or like some of the early scientific things that or like say Newton's stuff, where it took a couple of decades or whatever generation before that was really grasped. Like people kind of like when Newton was like, oh yeah, this is how this shit works. They're like, huh, yeah, I guess so. But it took a while for it to really sink in. Not until you get to like the, Einstein and those kind of guys that you really get to the consequences of Newtonian motion. Beer believes the same thing is going on with Ashby, that like Ashby says this stuff and is like, yeah, that smells right, but that we're still in the process of really working it. Well, we're not really in the process of working out what the actual consequences of law really are. So yeah, it's good stuff.
Matt, you had something to say?
Yeah, in terms of broad strokes, my favorite bit was when he goes so far as to even say, like there's like a fundamental like upper limit on like how accurate our measurement is going to be, and so like I like that he connects that to kind of a whole philosophy of science. I'm actually writing a thing for Cosmonaut on Philip Sci in terms of like instrumentalism. Basically, like you're not trying to find real reality. You'll never find real reality. Like for a lot of reasons, you can never really make a perfect model of reality. And so like just try to create models. Like the map is not the territory. All models are wrong, but some are useful. And like between like incompleteness and the fact and this quantum thing, like that says that like you're always going to have some amount of jitter, or even you could even say conservation of energy, because any measurement is ultimately a transfer of energy, and no transfer of energy is going to be 100% efficient. Like models, just have a whole bunch of models that are mutually contradictory. Try to coalesce them, but like you're never going to be right. So just try to make purpose-built models.
Right. And I think that kind of gets back to what I was saying previously in another discussion about the sort of lack or gap in understanding that we usually attribute to the sort of noumenal character of the thing in itself. When we look at it in terms of the upward limit on precision of measurement, we can see that this limit on understanding is actually a feature of reality. It's something that exists in the physical world. It's not just a kind of subjective problem. It is in fact something that's just like real.
And like everything is a noumenal thing related to something else, right? Like this is just a feature of systems in general, right? Like, so yeah, you're right. It's not peculiar to human perception. It's just a thing about information transfer and thermodynamics in general. So like, yes. it's all noumena all across the web, right? The whole thing,
right? I mean,
has this character to it. Yeah,
to the extent that it's like, what does noumena even mean when you think about it in a multi-perspectival sense? Because it's actually a feature of reality. It's not something beyond. It's not something beyond us. It's just what we are.
Indeed.
Okay, so let's get into it a little bit more then. So we begin with our discussion here of the anastomotic reticulum. It is back. So I think here we are talking about the sort of parity of inputs and outputs to begin with, right? That to get, like, ideally you want these things to match up. So, this is, again, something that's pretty familiar. Like, I'm trying to think of a good example here beyond the sort of typewriter example that Beer's using. I think, if you have a low quality signal and you put it through a really high fidelity sound system, you might actually end up with more noticeable noise in the end because there's not that parity between input and output. Does that make sense as an example? I think Shane you wanted to say something?
Yeah, I think that does make sense as an example. I just wanted to point out that in Ashby's introduction to cybernetics, when he gets to explaining variety, he explains it in terms of a game where two agents are playing a game on a board, and if agent B has enough output variety, like if it is able to actions to counteract every one of agent A's moves, then it'll be able to play the game fairly, or come to some sort of balance or whatever. It's a very contrived example. But if system B is constrained in some way, like it has one hand tied behind its back, it will be out of balance, and its output variety, like it will be not able to make the full range of moves. It'll have some constraint on it, and it will invariably lose the game because System A will simply outperform it at its move repertoire. Now, you could think of the same way for like flipping it around for input sort of things, that if System B was not able to discern the state of the board, or if there was some stochastic element to its sensing of the board, it would invariably lose to the more sensitive system. It's interesting that Ashby puts it in kind of game theoretic terms.
Yeah, I mean, that's a practical thing that comes up a lot in games. So, the famous example is first-person shooters. People on PC, they limit them from playing with people on console because they can use mice, and mice have higher variety than a console controller. So it gives them an unfair advantage and unbalances the game. Another one you could think of is like the way in which in RTS games, the computer has view of the full map, whereas you don't. And that can feel unfair because it's making moves with perfect knowledge of the map and you don't have it. So it's trying to unbalance things that way.
Certainly.
Okay. So I think that kind of makes sense. Rudy, please go ahead.
Yeah, right now I'm kind of thinking of the different approaches. Now we talk about game theory, how Deep Blue was very differently coded from whatever deep learning machine beat the champion Go player, because the amount of variety in Go is much bigger than the amount of variety in chess.
Yeah, absolutely. It needs to be adequate to the game. And yeah, I guess the game there would be considered the anastomotic reticulum that these two players are interacting through. Okay. So we talk about so to get to the anastomotic reticulum, says on page 40, final paragraph, the third part of the control system is the anastomotic reticulum, which connects the sensory to the motor plate, and there will be much discussion later of this component. For the moment, we will try to assess the scale of the problem that faces the control system for any complex organism, such as a human being or a firm, in terms of input and output. And now that these two terms are again mentioned in the same breath, let us note one more interesting fact. We spoke of the capacity of the parts of the control system to distinguish detail. On the input side, this capacity needs to be equivalent for the set of receptors and the sensory plate. On the output side, it should be the same for the motor plate and the effectors of action. So again, that's the thing we haven't quite talked about, is that there is on the input side, it's the receptors and the sensory plate. Those both figure into the calculation. It's not just the receptors. And then on the output, it is the motor plate and effectors of action. So those are both factors. Putting the whole control system together, then, we can see that this capacity needs to be the same for both input and output considered as a whole. So what I just said. The reasoning is exactly the same as before, and we are still assuming that the criterion is an efficient system. The common case in which, for example, the transmission channels by their nature degrade the information they pass will be different. Here, we shall need a greater amount of input data than can actually be used, and the surplus can be employed to offset degradation in the channel. Trying to find the part where he's talking about the additional complication brought about by the anastomotic reticulum. Does anyone remember where that is?
I think it might be getting on another page or two.
Yeah, I think so.
It's close to so he goes through the example of discriminating the letters of the alphabet, and it's like,
right.
Well, it's all fairly straightforward to us. I think it probably doesn't need to be gone over.
I actually had a question about that example. So he presents it as a binary system, but he talks also about comparing degrees of brightness to do the sort. And it seemed to me like that wasn't actually like digital. It was like more like an analog kind of thing.
So I think he kind of smuggles in an assumption somewhere that he doesn't fully explain. That he assumes that all 6 letters could be distinguished by their level of brightness rather than their shape.
Yes.
Just to keep the example simple. This is a kind of thing that Ashby goes over a lot of. That like the signal itself is analog. Like the reality of the situation is certainly analog, but we only have the ability to discriminate so many steps. So I think it's maybe somewhere else, probably in something we've covered for the show. There was the example of like the dimmer bulb, the analog like brightness of a bulb, and so it's applying a digital binary partition sort of thing to something that is ultimately analog.
Right. So it's basically rounding it into a 0 or 1 according to a certain threshold. All right. I believe, Matt, you wanted to speak?
I was just gonna say that though, yeah, because it was it took me a sec for that too, but it's it's an analog input, but it's a digital output. It's a binary classifier. Yeah. Yep,
got it. Okay, great. That just seemed a little bit ambiguous in the example there. It goes through that whole example. There's the whole issue of televisions. So talking about, so he says, we may start on this same problem of variety reduction from the other end. There are hundreds of lines in a television scanning system and hundreds of quanta of black or white dots transmitted to each line. There are thus, in effect, tens of thousands of binary receptors in use to generate a picture on a TV screen. Similarly, there are roughly 1 million binary receptors in the retina of each eye. No wonder, then, that either the camera or the eye can distinguish between 26 letters of the alphabet, for we have seen that the job could be done with only 5 receptors. So here's another key point. By using far more receptors than are theoretically necessary, we can in fact accommodate an enormous amount of confusion in the input. This point is analogous to the one about having 2 messengers carrying 1 message, although this time we are dealing with receptors rather than channels. Thus, people go on watching television pictures fairly happily and certainly with understanding when the picture is broken up quite seriously by electrical disturbance. Similarly, the eye will successfully read excruciatingly bad handwriting. This is because it has sufficient receptors to distinguish between millions of letters rather than just 26. And if we take all possible alphabets, including handwritten ones, into account, we may well need most of them. Yes, you can use very powerful receptor to deal with very noisy data, I guess is the point that's being said here, right?
Mm-hmm.
Yep.
I think SWR has their hand up. It's really hard to distinguish in this UI, actually.
All right.
SWR, do you want to go for it?
Yeah, actually, it was a question about analog and digital. I'm thinking it might make sense to ask it later, though. So carry on with this discussion.
Okay. And Shane, did you have something to say here?
Yep. The notion of sensory overkill is very, very interesting here because he's gone through the binary classifier thing and has actually kind of showed us that, like, if we have a string of bits, in many cases we don't actually need that many of them. Like, there's a wonderful compression going on there. Like, you can get pretty far with bits, right? Like 64 bits is enough to encode anything, that kind of thing. And so if you have sensory overkill, you can accommodate a lot of noise in the signal and still get somewhere. It's also interesting that this is an argument for the benefit of hypersensitivity. This is kind of like what Ashby was talking about with the difference between a brain and a shell, that like both of them are trying to defend the organism from threats, but a brain is hypersensitive in a way that a shell isn't. And so a brain is able to actively defend the organism in a way that the shell can't. There's a kind of a change in kind that comes along with the quantity of sensitivity, which I think is very, very interesting, right? At a kind of political level or a social level, we could argue for, societies that are more like the culture rather than like territorial state-like kind of societies, which were more shell-like, right? That like there is a benefit to the ultra sensitivity and sheer variety of capacities of a hypersensitive system.
This stuff is all really reminding me of John Boyd's theories of strategy, and just sort of like that hypersensitivity giving you a huge advantage in action.
Certainly.
Steve, please go ahead.
Just a couple of things. So one thing, like I couldn't help but think throughout most of this, like I don't know how many of you remember like throughout the 90s and early 2000s. So I listened to a lot of like music from, older music from the 20s through like the 70s, and like the constant like remastering of CDs that they kept pushing out. It's like, get the 8-bit, the 16-bit, the 32-bit like remastered, and it was just constantly like chasing this target and draining our, wallets. But I mean, that was like what I would keep thinking in the back of my head. And like one of the problems, of course, is like as you get higher fidelity remastering of these early 20s or 30s recordings, like there's a lot of noise in that stuff. And so you're absolutely running the risk of like amplifying that noise. And it actually makes it a more unpleasant experience and actually listening to some of this, which is funny. Because,
yeah, and like some of those early recordings aren't actually even that good, and like you're kind of better off with a 16-bit like 80s remaster rather than like the pristine kind of one, because you could kind of hide some of the ugly details behind a little bit of the attenuation in the middle ground, right? The 16-bit sort of era.
Yeah, and like you're seeing it even now.
Then
like,
you get the ultra high def one. Yeah,
this sort of backlash, right, of like all these DIY recordings that are being released on cassette, and it's like it's a way to just sort of punt on this whole problem, because now that we're stuck in a purely digital age, where so much of how we listen to this stuff is limited anyway, unless you really splurge on the really expensive ways of dealing with like getting back to high quality audio. But yeah, no, that was like that. Those were the echoes that I was seeing when I was looking at like, oh, you just need to keep increasing the number of bits in order to be able to like get more fidelity out of the real analog signals. It's, well, sometimes.
Matt, please go ahead.
Yeah, and then it goes into the active processing that he talks about too, right? Because there was a controversy that came out with like Disney like re-released like some old stuff, and like they realized they had a choice to make. They either display this thing that was never meant to be in HD, where you can see like hairs on the cell and stuff, or like they can change it a little bit, and then like that becomes like that's a non-trivial decision. And even if you use like something like these weird like super resolution algorithms that they're coming out with now, they really are mimicking what your brain is doing all the time. It's kind of wild, like it gets into very weird territory.
Yeah, absolutely. Third Creed, go ahead.
I was just going to say that maybe in that kind of thing, they're missing what the real signal was in the first place in any case. You know what I mean? Like, I'm not necessarily so sure that everyone wanted to hear the end of the envelope on a particular note or something like that. It wasn't like, you know what I mean? It's almost like, and this is probably just a completely, irrelevant point, but I was just thinking, that's not really I don't know how to talk about signal in the terms of like a cultural product like music, but it's not necessarily an audio product. Like part of the product is the time made and stuff. But anyway. Yeah,
absolutely. That's an extremely relevant point, right? Because it's like you've got to like a lot of this kind of technical stuff that Beer's going through here does presume that a signal and you've identified it or whatever. He's keeping it simple for the sake of exposition, right? But it's possible to misidentify a signal, right? Like it's absolutely possible to do that. It's possible to optimize for the wrong thing entirely. I mean, we're familiar with that in capitalism, right? Like it regulates a signal that none of us actually care about, and it refuses to regulate signals we do care about. So yeah, it's completely possible to just get it absolutely wrong at the like conceptual level, not even the sensory level, but just like the concept of what the sense even is can just be wrong.
Jeremy, please go ahead.
So yeah, I just found today an interview that Stafford did in 2001, and he's talking about neoliberal capitalism, and he says, the neoliberals have the wrong, he doesn't use the term neoliberal, but he's basically describing finance capitalism. And he says they've got all the controls wrong. They have this idiotic notion that if you just flip the knob back and forth on the interest rates, you control the entire society, and it's stupid.
And so that's kind of getting to, it's just not a sufficiently high variety control system.
Yes, and it's the wrong knob. Like, the interest rate doesn't care about workers. It doesn't care about the values of society. It doesn't take eudaimonia into account. It's just going to make the richest people in society richer or poorer, depending on how you turn the knob. And so he's like, that's just setting up a control system that completely ignores what we actually care about in society.
Yeah, definitely. I think that is one of the things about the post-73 austerity that was the most brutal, was just, basically the erasure of all those dimensions of society and experience as politically significant, and the assertion of monetarism as like like central bank independence, interest rate controls. That's the bedrock of society from now on, and we all need to get in line behind it. Just getting to the signal issue we were talking about again a little bit. I've been dealing with a lot of issues with 240p and 480i upscaling this week. So this is really relatable in terms of like, yeah, you could use a way more sensitive receptor for a signal like that, but you end up with all kinds of artifacts that show up in the picture. So yeah, it's really interesting. You can still, of course, discern what's going on. It's just you're ending up with artifacts that weren't there in the original. So that kind of speaks to that desire to have parity between the input and output. Okay. Let's see then. We get to the element of decision. The distinction between yes and no, between 0 and 1, is the element of decision. Managers may evade responsibility by giving equivocal or bogus decisions if they wish, or by making qualified utterances. But when the crunch comes, the answer is binary. And in fact, managers do use the process of dichotomous classification though rather informally. A managerial problem may have hundreds of possible solutions, and the manager may refuse to do more than say he thinks the answer will be towards one end of a scale rather than the other. This sounds extremely vague, but in fact, he's dividing the possibilities into two groups, which may not be of equal size, and thus leaving the threshold between the two groups muzzy. His people will go along with this for some time, performing actions which tend to push the situation in that one direction rather than the other, and trying to avoid the doubtful zone. But sooner or later, they reach a point where they cannot decide what to do, and the manager is presented with a narrowed down uncertainty. And so the process goes on, effectively splitting the universe of possibilities into two parts until one day the manager is faced with saying yes or no to some final proposition. It can be shown mathematically that the most effective way of going through a sequential set of decisions of this kind is to divide the possibilities exactly in half each time, but it does not matter much if the decision is not, in fact, equal. One may have to use an extra receptor, which entails taking an extra decision beyond the number which is strictly necessary, but the general procedure holds. Shane, go ahead.
So this, as a programmer person, this is all kind of fairly straightforward binary stuff, bit strings, they're great. I just wanted to throw it out there. Did anyone struggle with this example? Like, it is not super intuitive if you're not a computer person, just putting it out there. Does anyone need a further explanation of what's going on here? No, all good. Binary search. Fantastic.
All right. Good stuff. So he's talking about rate. It turns out, so this is on 45. It turns out then that the elemental decision between yes and no, 0 and 1, is the raw material of control theory. It is called a binary digit and contracted to bit. So, okay, talking about bits. Okay. So this next part here.
I think it starts to get interesting at the bottom, right?
Yeah.
Like, it's the very bottom of the page where nature takes its revenge, right?
Right. So there's the law of requisite variety. The answer is that we may devise variety generators and control mechanisms, just as nature disposes variety proliferators in proposing problems of control. So far, so good, but now nature takes its revenge. If we, the controllers, can generate very large numbers from a small number of components, so can nature. That is what variety proliferation means. Consider this. We said that we needed 5 receptors to read the 26 letters of the alphabet. Imagine then 5 light bulbs which can be lit up any number of ways. The fact that these 5 receptors will distinguish between 32 letters means that these 5 bulbs can generate 32 different patterns. And of course, if we want to know what our environment is all about, we have to recognize the patterns it displays. So if the outside world consisted solely of 40 light bulbs, we know from our previous argument that we could be presented with a million different patterns. True, it will take us only 40 bits of informational effort to distinguish between them. The situation is quite symmetrical, but the world does not consist of 40 light bulbs, but of milliards of things and events. Any comments on that? No? Okay, pretty straightforward. So we then get into this discussion about figure 9. And I think the point that was the most interesting to me here was the variety of the anastomotic reticulum. Does anyone have anything to say about that? Okay, let's talk about it a little bit more. So we have, Shane? Go ahead.
Yeah, so for me, it only sunk in at this point that the anastomotic reticulum, it's not just that it needs to accommodate the variety of the input and process it. It needs enough variety to map every possible input onto every possible output, that's where it gets truly explosive. Like, it's in that middle part in the anastomotic reticulum, because you're looking at like, a situation of n bits or whatever, and then 2 to the n states, whatever, that kind of shit. And then it's like, but you have 2 to the n to 2 to the n is the complexity of the interior part. That's where the thing really spirals out of control. It's like, it's not just like, because we can think of that thing of like going from an input to an output as a simple pipe. And you might be led to think, well, the pipe just needs to be as wide as the input, and that's fine. But it needs to be able to go from a world of patterns on the input to a world of patterns on the output, and that's a like a dimensional multiplication thing. It gets pretty obscene pretty fast. Yeah,
absolutely. So just getting back to our sort of our chess or Go example, I suppose that the game state or the board is able to accommodate an enormous amount of variety because it is a grid of possible variables that is operating in time. Like, the complexity is sort of moderated by the fact that the game state can change. Am I kind of getting at the right idea here? Because obviously chess and Go are very complex games, but the game boards themselves are very simple.
Yeah, I think there's something very interesting in that like there's levels of dealing with variety, right? Like, if you're an absolute novice to chess, you have to first deal with the variety of the pieces. You have to memorize what each of them does. Then you have the variety of there's this many squares on the board, fine. And then you're into, now we have the variety of all possible combinations of pieces and slots on the board. But then it steps up one level again into the variety of all possible transitions from every state to every other, to all adjacent states. And that's the kind of like the ultra high level of the game, meta game stuff that like chess geniuses end up playing, is they're not really tracing the individual moves of the pieces. That's happening, but it's kind of a sideshow. They're tracing trajectories through an abstract space of like, how do I transition from one board to another, and what's the variety of possible states that are 3 moves into the future? It turns out that's gigantic, like truly gargantuan. And so it's a navigational problem in many dimensions, including this like time dimension of like the sequence of variety changes.
Right.
It's maddening stuff at that level.
In a sense, like the board is kind of like a subsystem here, and the real anastomotic reticulum is like the all of the communication between the two players, because so much of what's going on in the game is not actually represented on the board. It's all in the mind games and stuff. Yeah. Matt, please go ahead.
It actually took me a sec for this because I think the typewriter is just not a great like example like for this, just because like it is like a 1-to-1 mapping, like as opposed to like versus like the chess versus Go thing, where you can kind of see why Go has such a bigger combinatorial explosion that like you can't brute force it, because like for chess, like there's actually a pretty small number of legal moves that you have for any given board state, and also there are fewer board states, and so just like everything's a lot more limited versus Go, where you have as many you have as many legal moves as there are like free squares on the board, and so like that's always just going to be like so much bigger. And I think it's the flexibility, that makes it the explosion. Where it's because like for any given state, times all the possible transition states. Yeah.
Right. Of course. Okay. So now we get into the impossibility.
I've had my hand raised for a bit, and I don't.
Sorry, it's hard for me to track because of how small the hand signals are. So please go ahead.
So I want to kind of say something Matt was saying, but in a way, like it's not only about say you have the example of 2 light bulbs. You have 2 light bulbs, you have 4 states. You have 4 other light bulbs, you have 4 states, so that you need 4 times 4. But then, like Matt was alluding to, the amount of moves you can do, it's not just about the amount of moves, but how many moves are legal. Because say if you cannot turn off both bulbs at the same time, that reduces the variety of the problem. And what I feel like in Go, you have way more moves you can make compared to chess. And that's where I think the reduction is happening, not so much in the fact that the chessboard is smaller. And so somehow this thing needs to encode history, and that helps us a bit reduce the scope of the problem.
Right. That's a very good point. The game board state can change so much and Go based on the sort of flexibility of the rules, what legal moves you can make. Third Creed, and then I'll go to Shane.
I was just going to ask if I understand that the anastomic, that the reticulum is just a very complex enough to be usually incomprehensible between an input and an output, some kind of incomprehensible mapping. Do I understand enough? Is there more to know than that, or is that, you know what I'm saying?
I think that is basically the outcome that we get to, right? Because we see next that we have the 300 employee example, which is far more than the 2 in, 2 out example that we saw previously, and it just becomes enormous. And so the question is going to be how to address that enormity. All right, so go to Shane and then Steve.
Yeah, I'll just bring this in quickly. Just something that Rudy said that reminded me of this, that is probably worth clarifying, that we're always talking here about discernible variety. So this is a point that Ashby leans on a bit more than Beer does, because I think Beer's just trying to get through a bit more material a bit quick. But Ashby uses this example of like, because the lights, right? But discerning the variety of you're watching a house, and the house has 4 windows. It's a square, like 2 on the top, 2 on the bottom, 2 on the top floor, right? And the people in the house will light up the lights with for a signal to you, basically. It's like a Paul Revere sort of thing. How many states can you actually distinguish? And you might think, 2 to the 4, whatever. But Crucially, if you see two lights that are laid out horizontally, left and right, you can't tell at a distance in the dark whether it's the top floor or the bottom floor that's lit. And the same goes for the vertical thing. So your actual, like, there is a variety to the real situation. And then there's the variety that you can discern in a situation. Now, if it was daylight, you might be able to distinguish that it's the top floor, two lights that are lit. And so you would have more variety to make the decision there. But the ability to distinguish things and to make decisions on them is always contextual and is often constrained by things that aren't really the fault of your senses in a way. Like it's circumstantial attenuation of variety, which means that the code could simply be scrambled for you. Like, oh shit, is it top floor or bottom floor that they've got lit? I can't tell because it's too dark. I don't know what floor it is at this distance,
Yeah, but conversely, like an owl would probably be able to discern that.
Yeah, definitely.
Yeah. Steve, go ahead. Then we'll go to SWR.
Yeah, I mean, I think, I'm sure that this is in many ways what the rest of the book is about, right? But like the notion of trying to figure out the different avenues for reducing the complexity just abounds, right? And you see it from even just going from the continuous space to the discrete space in terms of your N receptors. Like that's a decision you're making right away to constrain, to constrain and limit the problem. And then, and if you look at like decision theory and AI and things like that, like the fields are ripe with areas where you make certain assumptions about how the world works that can start reducing this complexity. We talked about things like the trajectories through time and how that massively increases the complexity, right? If you looking at things like, a good example from like reinforcement learning is, Markov properties, right? That you assume that how you are right now doesn't have anything to do, or it's irrelevant how you got there. Right, so you don't have to worry about your history. You can only worry about everything you see right now. And then, of course, like even that is not enough. So you have to start doing things like talking about probabilities and statistics and saying, let me reduce I don't have to know everything completely precisely, but if I get it 90% correct, then that's probably okay. And you can massively reduce, the 2 to the n to the 2 to the n variety that you get there. Unfortunately, when you start looking at things like that, it's like there's consequences, because even if you get it 90% correct, there's 10%, the 10% of people that, don't get healthcare or whatever, like there's real suffering there. And so like this constant battle that you're getting. And I mean, the problem that I've always had with it is that while there are certainly like, foundational and theoretical tools and assumptions you can make, so much of it ends up being so particular to the specific domain and task that you're working with that it's always very hard to extrapolate in any sort of general sense that is meaningful. And like it becomes so much more of an art than a science when you're actually trying to implement this stuff. I work in robotics, and one of the things that we constantly are dealing with is the fact that like specifically I work with like humanoid robotics, and they're expensive and hard to come by. So we have to rely on simulations. But simulations are making real decisions about what the world is actually like that are nowhere near accurate or reliable. So you end up designing your anastomotic reticulum to deal with a world that doesn't actually exist. And then when you try to take your software and then go put it on a real robot, then you pretty much have to start over from scratch, like more often than not. So it's like you make all these assumptions to try to simplify just to make progress, but it ends up being so, in practice, it ends up being so specific to the specific problems that you're dealing with. So, I'm looking forward to the rest of it, because the hope is that he starts to get into sort of general principles for dealing with this. But yeah, it's a constant battle, right?
Yeah, certainly. Certainly you can come up with solutions for these problems, but they do tend to be very domain specific and kind of rigid. So we'll go to SWR and then Rudy.
Yeah, okay, so what was just being discussed? Wait, can you guys hear me, first of all? Okay, great. I guess when I was reading this, when I came to the analog versus digital part, I guess I honed in there. I feel like there's something that makes me cautious about that distinction. And I'm wondering if Beer, and maybe it's too early to tell, but if Beer thinks that these are stable properties, right, of a input or output, or whether or not we should kind of look at it as, I guess, the relation between us being able to sense something and the thing we're sensing. When someone brought up the kind of the point that, depending on conditions, 2 or 3 light bulbs might look like one, right? And I guess that connects to this uncomfortability I have with the distinction between the two. And I'm wondering if anyone can kind of comment on that.
So you're speaking to the sort of stability of the inputs and outputs when considering a problem, like that these are actually quite in flux, and so the decision criteria kind of change.
Specifically, the stability of the distinction between an analog and a digital signal. Like I'm wondering, at a certain granularity,
Right.
does a analog system or signal turn into a digital signal? I guess that.
Yeah, I think you're on the right track there. Yeah.
Yeah.
I think I know I've been riffing on this for the whole call, but like it's kind of a thing that's more explored earlier in Ashby, or like I think Ashby leans on it a bit more, right? That like, yeah, we're dealing with ultimately analog phenomena, but we use heuristic, quick and dirty kind of essentially binary partition sort of stuff to try and deal with them. But you are right that like traffic lights at a sufficient distance will just look like a blur, right? Like it's there is the real will take its revenge on you ultimately, right? Like no matter how clever we think we are about our binary schemes. So we do have to bear in mind, right, that all models are wrong unequivocally, but some of them are useful, right? And like using bit strings, like strings of binary distinctions, is a very useful way to try to get to grips with something that will pay off if your model ends up in coherence with what the behavior of the real thing actually is. But it does leave open the possibility the behavior of the real thing might change, and you might be left in the dust, right? That your binary classifier might not work anymore. That's always a real risk.
Rudy, please go ahead.
Yeah, so just a bit on that topic, I feel like we're trying to get at, what is the problem here? And it's not really written, but the problem is basically choosing which of the 2 to the n, 2n of the anastomotic reticula is the better one. And being the better one is defined by many things. And some of the things it could be defined would be with respect to robustness. Like, you're saying, like, if I'm far enough, will my system break because it's not measuring accurately the signals? Or what am I optimizing for? Like someone brought up before, well, capitalism solves a problem, but it's optimizing for the Dow Jones index, not for the amount of people without home. So I guess it's like the subtext is there. It's not really written, but it's what they're trying to do, is trying to solve which of these ways of combining input to output is the best one. It's not that the map is 2 to the n, 2 to the n complex. It's that you're trying to find out which of the 2 to the n, 2 to the n maps is the better one.
Right. Yeah, that really reminds me a lot of like Otto Neurath's work on economics and sort of decision and what the criteria of decision are, all that sort of stuff. It's really interesting. Okay. So let's move on then. So we get the example of the company with 300 employees. So, the anastomotic reticulum needed to connect those together has the variety of 2 to the n, 2 to the n equals 2 to the 300 to the 2 to the 300. So enormous. I think we can all appreciate that size. So we then get into sort of like the computational capacity of matter in the universe, right, is the next thing that comes up. Or is it the Earth? We start with the Earth, right?
He starts with the kind of the kind of thermodynamic quantum sort of properties of matter, and then
right.
Like even if you turned all of the Earth into a computer, you'd still be nowhere near, or you'd be at the point of being able to get to grips with this one company, but you would have turned the company into a computer by that point. Like you would be a paperclip optimizer, just converting the entire universe into computer to barely keep up with yourself. Yeah.
Yeah.
I found the computational matter thing very bong grip, and I wanted to put on a Hawkwind record and, just kind of chill out with that thought.
I've definitely seen that example used before, like in other places to talk about computation and the limits to computation. Because I used to, have those like first year university student conversations with my friend and be like, you can figure it all out. You just need a strong enough computer and then you could compute everything and then that's the end of it. And I'd be like, no, you can't do that. And so, Third Creed, please go ahead.
Incredible.
I was just gonna say this whole thing of like using the cognitive capacity of matter itself and other things as a means of describing how to discretize things. Like, what is a thing? A thing is the thing we can understand, or something like that. You even said it. Someone said it in talking about saying maybe it was a relation. Like if you have an analog signal and you want to make it discrete, you have to have some way of some relationship you have with that thing, some kind of ability you have to understand. And I'm just really attracted to the way this, in a little bit in the next chapter too, when he starts talking about meta systems and how that how pervasive that like need to discretize, and how maybe all understanding or most understanding comes from some kind of discretization of that kind of thing. But just like this whole interplay between like complexity and the way that informs how you discretize things, and then how that informs, how you understand complexity itself. I think it's why these conversations get confusing sometimes, because it's so loopy, it's like self-referential.
Yeah, absolutely. There's like the complexity of your understanding versus the thing that's being observed, and it really gets into a loop. Rudy, go ahead.
Yeah, I think we kind of also alluded to this in the chat this week, that there's a difference between the number of possible states and the number of possible states you actually want to care about that contain information. And in Beer, he doesn't distinguish that yet. I mean, I'm talking about the first 3 chapters.
Yeah, very good point. Of course, this principle famously comes up in Cockshot and Cottrell's Towards New Socialism, where they use they just discard the states that aren't relevant and thereby make the problem of planning tractable. Very important point. I'm sure it'll come up at some point in this book. So now, so we'll get to the end. Page 50, he says, thus the anastomotic reticulum is no good by itself. Something must be done to make things work, to get the whole system under control. Proliferating variety must be stopped. The potential must be cut down and down, even though we cannot prove the best way to do it. There is no sensible way even to record and retrieve information on this scale, let alone compute with it. Heinz von Förster has given a graphic example of this memory problem. So he gives this memory problem of like multiplication tables, it has the results of multiplying all numbers up to only 10 digits by all other numbers up to only 10 digits. And the whole book ends up being 10 to the 15 centimeters thick. So obviously very unwieldy and like totally useless for actually getting an answer. But, a calculator can do it. Our brains can do it. Again, for the non-mathematician, okay, this is just about the size of the numbers. The bookshelf to accommodate this book will have to extend roughly 100 times the distance between the sun and the earth. A librarian moving with the velocity of light, declares von Förster, will require half a day to find a single entry in this book. The full-scale handling of proliferating variety is completely impossible for the brain of the man or for the brain of the firm. Yet both men and firms actually work. They do so. They must do so by chopping down variety on a mammoth scale. It takes more than an act of faith in electronic computers to achieve this. The question is, how does a system conveniently and effectively undertake this fearful task? The answer is by organization. So any comments on this sort of final concluding section here?
I think there's something interesting there that things work, right? But the firms work, they do so, and they must do so. And I think there's something a bit earlier in one of the chapters where he says something along the lines of a thing is, and it is in the sense that it works, but it performs, right, in the Pickering sense. Because if it's not, then it's not. It's like this is the only reality of being is in performance and in doing. It's the kind of thing he'll elaborate much later on, that non-viable systems don't tend to stick around long enough to be observed. They tend to just die. Interesting stuff.
Right. That is quite interesting. Such as of course the Soviet Union did not stick around very long at all, considering the resources and size it had. Jeremy, please go ahead.
So, not to do a spoiler, but further on in the book, he's talking about the viable system model with Salvador Allende. And Allende says, well, why isn't anyone else using the viable system model? And Stafford Beer gives him a bunch of cybernetics lessons, shows him the soundness of the science, and says, none of the people in the developed world are looking in this direction. If you organize your system with the proper organization, you could jump ahead of everybody because no one's looking at this. No one's thinking about the science of organization. And I thought that was really compelling. And it certainly persuaded Allende that this idea that this is a new way of organizing. There is science behind this. The methods are sound. And if you do this, you're going to be launched into an enterprise that no one else is doing. To me, as a socialist, that's tremendously exciting to me, this idea that there could be new methods of organization. I can't think of the word organization without thinking of Lenin, but obviously it goes in other directions as well. This idea that if you apply science to the concept of organization, you can create structures and methods that don't currently exist. And it's not a problem that they don't exist because you're using science to do these things.
Matt, please go ahead.
No, yeah, and maybe ultimately, we need to have a synthesis of Beer and Lenin, because I think it also goes to how at the end of the day, no matter how good your system structurally is, if you're not going for the right objectives and you're not encoding them in the KPIs the right way, it's not going to work. Maybe they should have tried to use some of this stuff to, I don't know, organize workers' militias and, loyal elements of the army. But, they were just so committed to, not going down that route. But, big fan, obviously, but he should have listened to Castro, should have armed the workers, and should have used the VSM to do it.
Sorry, I was also thinking that you could definitely do a synthesis between Beer and Boyd, because Beer saying you get that strategic advantage over your competitors. It really makes me think of Boyd again. Shane, go ahead.
Yeah, I mean, we need to look into Boyd, definitely. But yeah, the promise of all this and the kind of the reason for looking into Beer is, and the reason we're kind of standing for this, Beerian Marxism or whatever, is that if Beer is right, and I have a funny feeling he is, then the promise here would be to create social systems, social machines that just gigantically outperform everything else. And that, for the last couple of decades, we've kind of struggled with this problem of how do you outperform capitalism, right? You get that kind of post 68. I think maybe Kyle mentioned it the last time that when Deleuze is looking at this kind of thing and theorizing why is it that capitalism is so persistent, he doesn't look at it in these kind of quasi cybernetic terms, capitalist realism, all this kind of shit has seemed so just impenetrably huge and powerful. But I think in recent months we've seen strong evidence that it's really kind of pretty brittle. And, you know, if we intend to overthrow it, we should take the science of organization seriously instead of, you know, just like trying to resurrect some dead doctrine from the 1910s or whatever. That like the promise here is not just outperforming everything else, but vastly outperforming it. Like outperforming it in a way that like brighter than the stars. It is so much brighter that they all disappear from view when it's there.
Right. And you know, that's sorry, that's kind of always been the impetus behind planning in socialism, right? Is that there's this promise of unlocking an organizational structure, or finding an organizational structure that is going to be far more desirable than the local optimum we get from capitalism, right? And you know, this is I'm thinking here about like all of the socialist economics work that was done, like Yugoslavia and Hungary in the 70s and 80s. They were really interested in this question, and unfortunately, they became increasingly dispirited as time went on and started to believe that there was no such solution that would exist. But I think they were also not really looking at the sort of thing that Beer is doing here. They're really working within the paradigm of economics. Shane, go ahead.
I should also probably clarify that, like, I do strongly suspect that Beer is pretty much on the money with a lot of the stuff. But even if he isn't completely there on everything, I think there's more than enough material here. There's more than enough new stuff that is still comparatively new. Like, I mean, it's from 4 decades ago, and yet nobody's really looked at it. There's more than enough stuff to excavate that will pay off, even if he's not totally right on every single aspect. So I'm not expecting silver bullets, but I am expecting a substantially improved arsenal, like substantially improved, even if it turns out there's no silver bullets in there.
I mean, I think the best we get out of this is like a toolbox that we could use to create solutions. Because I like, you know, obviously there was no silver bullet during Beer's lifetime. If there had been, then he probably would have done more with it. But
we wouldn't need to have that conversation if there was a silver bullet, right? You know.
Yeah, I mean, I feel like you gotta learn this stuff before you can actually transcend it. Jeremy, please go ahead.
So we're going to find that chapter 20, the final chapter of the book, is going to be the most interesting to any sort of revolutionary communist approach, because he's going to talk about why it was that Chile was able to be shut down and what needs to happen to keep any sort of future social changes from being shut down the way that that Chile was. And a lot of it is struggling between optimism and pessimism, but I think it's the most difficult chapter in the book, but it's also a chapter about what do we do about the CIA? What do we do about the most powerful countries in the world just crushing any such enterprise? So I think when we get there, that's going to have the most potential on a political level, the 20th chapter.
Great, and we will look forward to reading that. But for next week, we'll be covering chapter 4. So, yes, just one more chapter again. The Organization of Unthinkable Systems, which is a really great title. And I look forward to seeing all of you next week, same time. All right.
Yeah, thanks everyone. It's been good.
Thanks, guys.
Bye-bye.
all.